Okay, so today we're going to talk about the formal definition of a derivative. But before we go into what a derivative is, I want to think back to something that we're very comfortable with it, which is slope. So thinking back, slope we know is the change in y over the change in x. So if I have 2 points on a line, I could find the second y value, y2 minus y1 over x2 minus x1. That would give me the slope of a line. But what happens if instead of talking about the slope of a line, we're talking about the slope of a function that's not linear? So thinking about this function has different slopes depending on where you are on the function. It's possible if this keeps curving up that over here it might have a negative slope. Here it might have a slope of 0. Over here it has a positive slope. The slope is getting steeper. So you'll notice that the slope is changing throughout the function. So now I'm going to pose the question, how could I find the slope of this function at that exact point? And let's just call that point x naught. Now, based on our definition and understanding of slope, what we need are 2 points. And I'm asking to find the slope at 1 point. So let's just think a little abstractly right now. Let's identify another point, and let's just say that that is h units above x naught. So that value is x naught plus h. And if we were going to find the slope of the line going through those 2 points, or the slope between those 2 points, we could just use the same slope formula that we did in Algebra 1. So y2 in this case is going to be f of x naught plus h. y1 in this case is going to be f of x naught. x2 is going to be x naught plus h minus x naught. And you'll notice that these two x naughts are going to subtract to be 0. So that gives us this equation right over here. The slope, or the change in y over the change in x, of our function between the points x naught plus h and x naught. So if you think back to the original question that I asked, I wasn't asking for the slope between those 2 points. That actually gives me the slope of a secant line, the slope in between 2 points. What I was asking for was the slope at that point x naught. Since we chose h to just be some arbitrary value so that we could think about this abstractly, what we're really looking at is what happens as h gets closer and closer and closer to 0, meaning that the space in between these 2 points is getting almost non-existent. And we have spent the last 3 lessons working up to this idea. How can we think about this? We could think about this using the idea of a limit. So we're going to look at the same slope, the same delta y over delta x as we did for the secant line, except we're going to take the limit as h approaches 0, meaning that space, again, is getting smaller and smaller and almost non-existent. And that will help us identify the slope at a particular point, at a particular x value. And that is a derivative. A derivative is the slope of the tangent line, the slope of the line that touches that exact point that we were looking for. Something else I want you to think about is that we started by saying that since this function isn't linear, the slope is going to be changing. Sometimes it's negative, sometimes it's positive, sometimes it might even be 0, which means that when we find the slope of the tangent line, or the derivative, as we're defining it here, we're actually going to be given a function that we can use to approximate the slope at any given value. So what we're going to be doing is we're going to be finding a function that represents the slope at which we could evaluate it given a specific x value. Okay, so let's talk through some notation. All of these notations mean the same thing, and you will see them used interchangeably. We'll talk about sometimes there are circumstances where one version may be better than another, or one notation may be better than another. But right now they all mean the same thing. This is f prime of x. That means the derivative of the function f evaluated at x. dy dx, which is the derivative with respect to x of y. dx, ddx of f of x, and y prime. All of those are different notations that really mean the same thing. We will often be evaluating our derivative. So our derivative is a function. We may want to evaluate it at a specific x value. Here's one notation that you may see for that. dy dx when x is equal to 3. You might also see f prime of 3 telling you to substitute the value of 3 in for x into the function that you found. One last thing to note before we jump into some examples. Not every function has a derivative, and not every function has a derivative at every value. Thinking about the fact that the derivative is the slope, a vertical line does not have a slope. So if there is a curve that would have a tangent line that would be vertical, there would be no derivative at that value. And we'll talk about some other cases where derivatives don't exist as well. So let's walk through some examples. Something I want to point out is that if you took Calc AB last year, or you did something to brush up on calculus over the summer, you may know some shortcuts. You are not allowed to use shortcuts. We haven't learned them yet. We will very soon. But the directions here specifically say use the limit process, which means some of you are looking at number 1 and you already know that the derivative is 2x. That's great. That means you're mentally checking your answer, but you need to show the limit steps to show the work to get through that process. So we're going to set this up using the definition of the the definition of the derivative. So I rewrote that definition down at the bottom. So the limit as h approaches 0 of x plus h quantity squared, so I just substituted in x plus h, minus 2 minus the quantity x squared minus 2. Make sure I don't forget my parentheses there. So I'm going to do some algebra to simplify the numerator. So I expanded the numerator, x plus h quantity squared, and now I'm going to combine like terms and simplify. So the x squareds subtract out in the numerator, as do the negative 2 and positive 2. That leaves us with 2xh plus h squared, and I'm going to go ahead and factor out an h, and you're going to see that that h simplifies here. Now, as h approaches 0, this term is approaching 0, so we are left with 2x. So what we can say is that f prime of x equals 2x. It then asks us, if you can read underneath all of that, to find f prime of 3. F prime of 3 means I'm plugging 3 into that function, which is going to give me 6. F prime of 3 equals 6. So I went ahead and cleaned that up a little bit. You can show a lot fewer steps than I showed that first time through. I just wanted to make sure I didn't lose you along the way. So if you need to go see some of those steps, just rewind the video. And I'm going to go ahead and set up number 2. Feel free to pause the video and try and work through number 2 on your own. So the setup, the limit as h approaches 0 of the square root of x plus h minus the square root of x over h. Now right now, if we tried to use direct substitution, we would get indeterminate form, which means we need to use some sort of algebraic tool to help us here, and that's going to be conjugates. So you're going to go ahead and multiply the numerator and the denominator by conjugates and then simplify. So that's going to give us the limit as h approaches 0 of x plus h minus x, just using the difference of squares when I multiply those conjugates, over h times that conjugate. And then I'm going to notice that these x's are going to add to be 0, so all that's left in the numerator is h, but I also have an h in the denominator that I can divide out to be 1, so all that's going to be left in the numerator is 1, and the square root of x plus h plus the square root of x is going to be in the denominator. As h approaches 0, remember x is not approaching 0, just h, that's going to leave me with 1 over 2 times the square root of x, so there's my derivative, f prime of x is 1 over 2 root x. If I'm evaluating that at x equals 4 to find f prime of 4, the square root of 4 is 2, so that's going to give me 1 over 4. So notice on number 3, we actually have y as a function of t. That doesn't change the process that we're doing at all. You're just going to see slightly different notation here. So when we take the limit as h approaches 0 of 2 over t plus h minus 2 over t all over h, instead of writing that as a complex fraction, I just wrote 1 over h at the end of it. What we're going to need to do here is we're going to need to find a common denominator and combine these fractions. So that common denominator is going to be t times t plus h, so we're going to multiply that by both fractions to combine this to be one fraction. I'm going to move my 1 over h to the front. I'm kind of afraid I'm going to forget about it if I don't. That's going to give me 2t minus t. That's going to add to be 0. So I now have negative 2h in the numerator. The h in the numerator can divide with this 1 over h. So that leaves me with negative 2 over t times the quantity t plus h. As h approaches 0, I'm just going to have t squared in the denominator. So dy dt is going to just be negative 2 over t squared. And that function allows me to find the slope of the tangent line at any point along the curve. Now up here it's specifically asking me to find out what happens when t is 3, so dy dt evaluated when t equals 3 is just going to be negative 2 over 9. Number 4 is a little tricky. So setting that up, the limit as h approaches 0, cosine of x plus h minus cosine of x all over h. And I'm going to give you a minute. Try and use that hint to see if you can expand this out, which may not seem logical, but in the state that we're currently in, we can't simplify. So we want to get this into something that we know how to simplify using limits. So in red, you can see that substitution happening using that trig identity. Now what I'm going to do is group the cosines together and the sines together. And I'm actually going to split that limit into 2 separate limits. Since I'm talking about multiple functions, we can use those algebraic properties for limits to split this. So why am I doing all this? Within what we have now, we have 2 different trig limit properties that we are allowed to use without having to prove them, that we proved in 1.2, 1.3, I forget. So we know that the limit as h approaches 0 of cosine of h minus 1 over h, that is 0. We showed that in 1.2. That actually means that I'm multiplying 0 by cosine of x, so this entire term right here is going to go to 0. Now, the reason that this is minus the limit of sine is because I just took this negative sign here and I threw it in the front. You could have it on the inside, it doesn't matter. I have 0 minus this limit as h approaches 0 of sine of x times sine of h over h. Well, sine of h over h, the limit as h approaches 0 of that, also from 1.2, we know to be 1. What that means is, as h approaches 0, this portion approaches 1. That just leaves me with sine of x times the negative that was in front, so 0 minus sine of x. So the derivative, the slope of the tangent line, is the function f prime of x equals negative sine of x. If we were going to evaluate that at pi over 3, you're just substituting in pi over 3, which is going to give you negative root 3 over 2. So we are going to talk about shortcuts. You're not going to have to do this every time I ask you to find the derivative of cosine of x. But if I ask you to find it in this way before we have identified our shortcuts and tricks that you can just use, you should be able to go through this limit proof or this limit justification of why the derivative of cosine of x is negative sine of x. The very last thing we're going to talk about today is the alternate definition of the derivative. So for every problem we just did, 1 through 4, the very first thing we did was find the limit as h approaches 0 in order to get a function that represented the derivative at any indicated value. Well, what happens if we didn't need to know it at every single value? If we didn't need to come up with a function, we just needed the exact value of the derivative, meaning I know what that h value is, or I know what that x naught value is that I want to find the derivative. In that case, we can sort of cut out that middleman. We can cut out the portion where we're finding the function and jump straight into the part where we're actually finding the value. So tying this back to slope, we're looking at the change in y over the change in x. We're looking at f of x minus f of c over x of c, just looking at the change in y over the change in x. Now again, that would give us a secant line. If we're looking for the tangent line, which is what the derivative is, we want to see what happens as x gets closer and closer and closer to our c value, which is where this comes from. Sorry, the spacing is messed up under that. So the limit as x approaches c of f of x minus f of c over x minus c. So you are using this when you are specifically only being asked to find the derivative at a particular value, not to represent the derivative as a function. So that's the key distinction between this and the formal definition. So let's go ahead and work through this. So for number 5, we're looking for the derivative when x equals 3, so the limit as x approaches 3, of x to the third minus 3 to the third, because we're substituting in 3 to our f of x, over x minus 3. Now you're going to need to use the difference of cubes formula to simplify this, because right now I'm getting indeterminate form, so you need to use algebra to simplify. So if I factor the numerator, the x minus 3's are going to divide out. Now I can use direct substitution, and that's going to give me 27. 9 plus 9 plus 3. Whoopsie, that should be a 9. 9 plus 9 plus 9. Let's make sure we factor correctly. All right, go ahead and pause and try and work through number 6, our last problem for the day. So the limit as x approaches 2 of x to the third minus 2x squared minus 1 minus, and then we're actually substituting 2 into that. So let's simplify that. 2 to the third minus 2 to the third minus 1. Make sure you remember to distribute that negative sign. And then let's go ahead and rewrite this. Notice that when I distribute that negative sign, this is going to become positive 1, and I already have a negative 1, so those are also going to add to be 0. Now I can simplify, I can factor an x out of the numerator, which is going to simplify because I can't use direct substitution right now. So those x minus 2's are going to divide out. Now I can use direct substitution, which is going to give me that f prime of 2 is going to be 2 squared, which is 4. So key takeaways from today: the derivative is the slope of the tangent line. You can find that using the definition, the limit as h approaches 0 of f of x plus h minus f of x over h, and then simplifying. That gives you the formal definition. You can use the alternate definition only when you are looking for the derivative at a particular value and you don't need that function. So make sure you review this video as needed, pause, go back and rewatch.